Welcome back to Anton Math, and in this video we're going to be talking about some of our basic set operations, the most common set operations that we use when we're talking about sets. So let's start off, let's let S, T, and R be sets. I'm not sure I'm going to use R, but just in case. Now the first operation I want to talk about is called the union. It's just called union. And we denote a union, let's say S union T, in this way. It's kind of this U. It's not actually a U, it's more like a cup kind of symbol. You can have a set called U and it'll look a little bit different. But in set notation, what this is defined as, this is going to be all of the elements X, where X is an element of S, and X is an element. Sorry, did that backwards. X is an element of S, or X is an element of T. Right, so this is pretty much, we're gluing these two sets together. We're taking all the elements of S and all of the elements of T and making a new set that just contains any element that's in one or the other. Now remember, this is mathematical OR, so let's just say, 2 was in S and in T. 2 would still be in here, right? It's not an exclusive OR. It includes the case where X is in both S and T. My only requirement is that it's in at least one of them, right? And we also have kind of an opposite idea in a certain sense, the intersection. Now the intersection of a set, I'm going to denote this S intersection T, so it's kind of like the union sign but upside down. And that's going to be defined as all of the elements X, where X is in S and X is in T. Right? Remember, this is OR, this is AND. So my requirement here is that it's in both, right? If it's in S and it's not in T, then it's not going to be in the intersection. The intersection is the set of all common elements between the two sets, S and T. Now we also have a difference. The difference can be denoted a couple of different ways. Sometimes you'll see it S minus T, but this is the same thing as S and then it's kind of / T. And what this means is this is going to be the set of all of elements that are in S and are not in T, right? So all of the X where X is in S and X is not in T. So basically we're taking the entire set S and then we're removing any elements from S that happen to be in T. Okay? And then one last kind of operation we're going to talk about is called the complement. Complement. Now this is denoted a couple of different ways. I could write this with X with a bar. Sometimes it'll be S with kind of this little tilde on top of it, and sometimes it'll be S with this little C. Right? Depends on what text you're using. These all mean S complement. And S complement, this is going to be with respect to a particular universe. Right? We talked about in the last video, we talked about universe, but this is defined to be the universe, and then I take out everything that's in S. Right? So in other words, this is the set of all X in whatever universe I'm talking about. So maybe that universe is rational numbers, maybe that universe is real numbers, whatever it is I'm talking about, where X is specifically not in S. Right? So any other S will do as long as it's within that relative universe. So a couple of notes real quick now that we have some terminology. Note that I can write this S minus T, I could write this as S intersected with T complement, right? You see that? So everything in S that's not in T, well, that's the same thing here. This is everything in S that's also in T complement, or that's also part of the set of things that are not in T, right? So this is an equivalent idea. We say that if S intersection T is equal to the null set, right? So in other words, if S and T have nothing in common, S and T are called disjoint. All right, these are disjoint sets. For example, the set of all chairs and the set of all bowling balls are disjoint sets, right? There's no chair that's a bowling ball unless somebody has made one that I don't know about. Okay, so we call those disjoint. It means they're two sets that have no commonality. None of their elements are shared. Okay, so now I've gone over a lot of terminology. Let's go ahead and do a quick example before I end this video and go on to the properties of these operations. So let's just say I have my S is equal to, I don't know, 1, 2, 3, and my T is equal to 2, 4, 5. Okay. So given this, we can calculate out some of these things. My S intersection T, remember that's going to be all of the elements that are in both S and T. So that's going to be the set containing only the element 2, right? We see that 1 and 3 are not in T. So 2 is the only element that's in both S and T. Now the union, remember the union is going to be all elements that are in S or T. So 1, 2, 3, 4, 5, right? This is why I keep saying this is kind of like gluing these together, right? This is the set of all elements that are just in one of these sets. Okay, and we take out any repetition. 2 is in both, but I'm not going to write 2 twice, right? We know that with sets in general, we don't include any repetition. Say the difference, S minus T, that's going to be equal to all of the elements in S that are not in T, right? So in other words, 1 and 3. And the difference, T minus S, that's going to be all the elements in T that are not in S. So 4 and 5, right? Because they share that 2. So something kind of neat to note, notice that if I have this S minus T union with T minus S, that's going to be the elements 1, 3, 4, 5. But that's the same thing as the union of S and T minus the intersection of S and T, isn't it? It's kind of interesting. Now we call this an identity, right? This is something that's an identity, and in the next video I'm going to go over a lot of our set operation rules, a lot of these identities, so we can kind of use these tools to simplify the same way that we would use in algebra to simplify an algebraic statement. We can have these long strings of these set operations, and we can use some of these rules in the next video to simplify these strings into something much more compact and much more simple. All right, we'll see you there.